what we're going to be going over here are Lagrange multipliers, and we'll do it from the visual perspective. We'll throw the math in at the end, but we'll do it in terms of a production function, which is really similar to the Cobb-Douglas production function. Okay, so this is our production function here, and what we want to do is we want to maximize our output, and we want to do it the most efficiently here at the least cost here. So for our production function, let's just say here on a per unit basis, we're selling a product here for $1,400, and we take that times the material and labor inputs here raised to some exponential amounts here. And then from that, we're subtracting the unit cost here for material and unit cost here for labor. Okay, so what we're trying to do is we're trying to maximize our revenue here through our revenue portion of our production function here, shown over here, per unit revenue on a per unit basis times material and labor here. But what we have to do is we're subject to a cost or a budget constraint. So our costs that we have here on a per unit basis that we're subtracting from our revenue here also have a constraint on the budget. In this case, we're using it in terms of this G of M of L here. We'll use that in terms of our constraint function here, and this F in terms of material and labor here is for our revenue portion here, or output. But our cost constraint is $40,000. So we can only spend $40,000 based on our cost here, $350 for material and $200 here for labor on a per unit basis. So this is where that Lagrange multiplier is going to come into effect. Okay, so the first thing let's go look at here is what we would look at the vector field first for our output here. And really that shows the direction and the magnitude of our output here at a point. Okay, so what I'm showing here in 3D here, we've got our output Q here, or that would be like our revenue here, showing our vertical axis. And then along our lower axis is we'd have material and labor. And what I'm showing here on this production function, we're just looking at it at a side profile here. These little red lines are our ISO lines, or equal product lines. And the function here is that what we had here, 1,400 for per unit for our what we sell the product for times material and labor inputs here. And then we have here this yellow, showing this yellow plane here. That's our cuts through our ISO curve here at a certain output level. Now, what's interesting about this is these arrows here. Those are our vector field based on that function we have here, that revenue portion, or material times labor times our output here. So the idea is here, the bigger the arrow, the greater the output at that point. And also with the arrow here, the larger the arrow, the greater the output, but it's pointing in the direction of the greatest output. So if you look at it in those terms, and what I've done here, I've used MapleSoft here, you can look at it and get a pretty good idea what's going on, because you can rotate this 3D plot out, and you can see which way those arrows are going. But what we have to do is we have to make sense out of this vector field here. And we do that by going over here. This is the case here where we're going to be using that Lagrange multiplier here to determine come up with the most efficient output here for our combination of material and labor. So what we do here with that vector field that we have here, we're going to turn it into gradient vectors at that specific output here. So again here I got that ISO curve. That's that ISO curve, equal product curve at a specific output, shown in yellow here, and it's slicing through our production function here. So these red arrows here are our gradient vectors here. Now remember, a gradient vector always points in the direction of the greatest output. So I've got it plotted here, but they're also on size here. The larger the size, the greater the output at that specific point here. Okay, so the key is here with these gradients, they give the direction and the magnitude of the greatest output. So what we want to, and you can see here, our greatest output is going to follow up this yellow arrow coming up here, because this blue background with our red lines is our production function for that revenue portion here, and those red lines are those are ISO, or equal product lines for at a certain production level. So again, we want to turn our vector field that we had here into a gradient field, and that's going to give us the magnitude and the direction of the greatest, or the output here, or the most efficient output that we're looking at. Lowest cost, maximum output. That's what we're going on. Okay, so those are our gradient vectors, but this is what we're coming up against here. So moving over here, we're going to add in this cost constraint, this vertical, sort of goldish vertical plane that's cutting through here. That plane is cutting through exactly at the same point of our iso curve, or our output plane here, and there's going to be some tangent point and some tangent line that's we're going to have to come up with here to understand where we put in this Lagrange multiplier that we have. So this gold line here, that's our constraint. That's that per unit cost here for material and labor at that budget. 40,000 here, so you can see that we have to subtract that here from our material and labor inputs, that 40,000. So what we're showing here is, again, it's moving up in this direction here. This is that g of x, or our constraint here, and this is where that lambda is going to come into play here. So we've got our gradient vectors here, and they're bumping up against our constraint here. You can only put out, or based on that gradient, or our greatest direction of our greatest output, we come up against it, but we bump up against our constraint. So that's what we're talking about, and that's going to involve this lambda. Okay, so let's just go up here and just make a comparison here. Again, what I'm showing here, these red arrows here, that's our gradient field here, and that's our output. That's the direction and magnitude of our output Q here, and that's the direction of the greatest output. So they're pointing in the direction of the greatest output here. Okay, so that's what we're going to be working with, and when we're working with this lambda here, this Lagrange multiplier, we're working with gradients here. And just to make a comparison here too, remember I talked about those vector fields here on our function. You can see those arrows here. They're pointing in really different directions here than our gradient field here. The vector field here, Q output, is a direction and magnitude at a point. At a specific point, they're pointing. At that particular point, they're showing the greatest output here. Whereas these red arrows here, those are the gradient arrows, and they're showing the direction of the greatest output. They're not just taking a point. They're actually looking at the direction here. So that's what we'll be working with. Just to get an idea here, you can see the vector field here is veering off in different directions, but with our computer packages here, it gives us a good visual understanding of what's going on here. Okay, so now we'll move on to our next calculating our Lagrangian. Okay, now for calculating and understanding our Lagrangian multiplier. So we'll start with our 3D diagram here. So what I'm showing here is that production function here. That's really a side view, and I got those iso lines here, those equal product lines here, and that's really that revenue portion here of our function here. And we had a certain output level, and that output level is really based on the fact that we're coming up against this cost constraint. So the cost constraint is sort of this mesh area, this vertical area here, plane cutting through the production function here at a specific point here. And what's happening here? The output level here and our coming up against our cost constraint, they're going to share a specific point here, an equal point here, and it's going to be a tangent point that they share here. And along with that, they're going to have a tangent line. So this is what we have to determine here. We're going to look at it in terms of this tangent line and this tangent point. They're going to share this tangent line, and that crosses right up at the point here. At this tangent point here is really our maximum output. And that's where we're going to work with this Lagrangian. So what they're doing is both our constraint here and our output here are really sharing an equal slope or maximum output at that particular point. So let's see how we get to that point here. Okay, so first looking at our production function here, looking at that output, that revenue portion here. So going down to our output level here, this yellow surface here, that's cutting through our production function here based on the fact that we are coming up against that constraint. So the key is here, that iso curve here, at that particular output level here, we have an iso curve, and this is the idea what's going on here. You start out over here, say working from our right and going to our left here. So I start out on our right and I follow that iso curve along here. So it's a little hard to see here because we're not looking at it from the elevation here. But what's happening is here when I start at the far right, as I keep moving and moving over towards the center here, my slope keeps increasing. It's going to get steeper and steeper here as I move into the production function here up to a certain point. So it increases to a certain point. Then when I get to that point, as I move further and further to the left here, that slope is going to be decreasing. So the key is here. When we get past that point here where it starts decreasing, we want to move back to the point here where we had our max. That determines our maximum increase here. So we're dealing with that isopath, that curve, equal product curve coming along here based on the fact that we're coming up against the constraint here. So this is where our slope is going to be at the maximum at this point here. So if what you want to do is you want to keep the ideas here, you just keep moving up and up and up that curve here until you meet the maximum point, and then if you go past that, you're going to move down and down further. Your slope's going to decrease. So you're looking at the change of slope here. So you want to we're going to be determining the point here where we got the maximum slope based on that output that we have here on the constraint. Again, the material and labor are shown here on your lower axis here, and our output is actually moving up this yellow area here. That's really our maximum output. So that's what we're looking at when we're talking about the equal product, coming up against that maximum point here where our slope essentially is at a point here where it meets its maximum, and then below that it goes to a minimum. Okay, so that's looking at our output. So let's move over here and look at our cost constraint. Okay, so I'm looking into our production function here, and again, the goal is to climb as high as possible, but you can't move any higher than that constraint. So I'm showing that cost constraint here, that g of x here, that cost constraint. That's our vertical cost constraint cutting through our production function here. So you do the same thing here. You're looking for the change in slope. It looks like the slope is pretty steep here, but in fact it isn't, because you're at a low ISO curve here. And what's happening here is you move up and up around through this, looking at this curved area here, as you move up and through our production function here, your slope keeps on increasing here. And then you're going to meet, the same as you had here with the ISO curve here, you're going to come up at a point here where your slope is at its maximum here. And then when you move past that point, say again we're moving to our right, from the left to the right here, the slope is going to start decreasing. It's going to decrease, decrease, and decrease. So again, you want to move back here. When it starts decreasing, you want to move back to the maximum point. Same thing, when you're moving from the right to the left here, you want to keep increasing it till you come up to the maximum point here. Okay, so really we're looking at the change in slope. We want to get to the slope at the maximum point. So the key is here, if we go back and look at our ISO curve here, so what you want to read, the slope of the constraint line equals the slope of our level curve. Now the constraint line was that vertical up constraint here based on that cost function that we have here, based on a $40,000 maximum amount in this case of combination of material and labor cost here. So you're looking for equal slope of the level curve and our constraint here, the equal slope between the constraint line and a level curve. They're going to have parallel tangent lines, and they're going to share the slope. These tangent lines, just going back here and looking at them, they are actually parallel here. So that's really the key that we're looking at. And when we're going to look at the the output here, we're looking at the gradient here. We're talking about always going perpendicular. We go perpendicular to the our ISO curve here, always gives us the greatest increase in what we're looking at. So we're going to look at that here. Okay, so we understand that by going through and checking our slope, they're going to share an equal point here where the slope is the maximum between our production function here, slicing this output level, slicing through our production function, and this vertical. This is more or less a horizontal one, where this is a vertical one cutting through our production function. So they share that tangent line and that maximum slope. So that's the key that we're looking at here. So if we go down here, now let's look at what we talked about. This is what we're trying to get to. We're trying to get to this Lagrangian multiplier here, and it's this lambda symbol here. You can use any symbol you want, but they usually use lambda in this case here, your Greek symbol here. So what you want to do here, if you're looking at it, again, we're looking at it looking at to our production function here, and there's our equal product curve here slicing through it here. This is what's happening. The gradients are parallel and they're perpendicular to the level curve here. So we found our maximum point here, and we know that the production our revenue function and our constraint share the same tangent line, and they share the same slope, that maximum slope here. So what we're talking about here, we're going to have to calculate the gradients here. So we have the gradients here for, I'm showing g of x here for our constraint. That was that vertical cutting through our plane here at that point. And then we have the output function, the f of x here. So what we're going to find out is that this constraint here, in this case, it's actually greater, the gradient. The gradient is a value or a scalar value here between the output here and our constraint here. And we're going to find out that our output is a little bit, this is where that Lagrangian, the difference between our constraint here, that gradient for our constraint, and the gradient for our output, that difference, you can see I've shown here in yellow, there, that difference here, that length here, that difference, that's the Lagrangian multiplier. So that's a really important, and that's how we can come up with our maximum solution here for our best use of our resources here for material and labor, the best combination for our maximum output. So that point here is following up at our maximum output. So just going and looking at doing our calculations now. Okay, so we're not going to go through all the calculations, but just to set up our Lagrangian here. So here's that here's our revenue portion here, and then we subtract from it. This is where that lambda or that Lagrangian multiplier comes into effect here. So we're going to be subtracting here our cost constraint, and we're going to take a cost constraint here times that lambda. That is the key here. That's the key to the whole thing. So our cost constraint here was $350 per unit of M plus $200 per unit for labor minus our constraint. And we're constrained to $40,000 maximum to spend on material and labor. And you take that whole quantity here times that Lagrangian. And then you subtract this quantity and the Lagrangian from your revenue portion. So this is our output shown here. Here's our constraint along with our Lagrangian. So really you come up with 3 equations, 3 unknowns, and again I did it through MapleSoft, and what you're going to come up with is this. You're going to come up with a solution where you're going to get a certain quantity of labor, in this case 78 point some fractional amount here, and quantity of material here, 69.68 here. And then along with it, you're going to get this Lagrangian here. And this Lagrangian is called Lagrangian multiplier. So what is that? That is equal to 0.96608 here. So it carried out to quite a few decimal points here. Actually, the computer carries it out very, very far here, just showing 5 decimal points. But it's key here. So this is what they call the Lagrangian multiplier here. And really, we needed this Lagrangian multiplier here because we had to come up with 3 equations and 3 unknowns, and we're dealing with this M and L here as fractional amounts times each other here, and you're coming up with a multivariate calculus figure here. So if you didn't add the Lagrangian, and the Lagrangian is added here so we can add this cost constraint, and it's adding an artificial variable, a third variable here, so we can solve for material, labor, and our Lagrangian. Because what you're going to do when you got these type of equations here, you might come up and the answer would be, well, it solves for M in terms of L in terms of M, and you don't get a specific number here. So Lagrangian was really for that key item here is to come up so you can get a specific, come up 3 equations, 3 unknowns, and it had to be added as an artificial variable so you can get the actual quantity of output rather than M in terms of L and L in terms of M, where you wouldn't get an exact quantity. Okay, so this is where the Lagrangian comes into play to get the quantity, get your exact numbers here. But then secondly here, and it's quite important here with the Lagrangian, so let's look at it in terms of that gradient. We were talking about that gradient for this whole lesson here. So the gradient is really the partial derivatives of our Lagrangian function here. That Lagrangian function, partial derivatives in terms of L, M, and the lambda or the Lagrangian here. So what I've done here is I just did it through Microsoft, and I have for our output function here, the gradient for output function, we would have had some quantity here for material. And what I'm doing here, I solve this for the partial derivatives here for that our output here. All right, so we've got some material here. All I did is I go in and I take the solution here, I substitute it into the gradient that we have here and evaluated it. So for our material as a partial derivative in terms of our material here, our gradient, when I plugged it in here, these numbers as 78L, 69M, and put it in here, I get 338. So that's my gradient, and that's what for the material portion here, and that's what it's a scalar amount that's pointing in that on that iso curve, perpendicular to the iso curve at that point. And then for labor, I did the partial there, and I get 193 here in labor. So you total those together, and my gradient here is 531.33 here. So that's the key here. Okay, so now we've done that for our output. So now for gradient for our constraint here. That was for output. Here's our constraint G here. Again, it was evaluating here. That was that 350. This is the partial derivative. 350 here for material plus 200 for labor. That's just, I know that because I knew that was the partial derivative for our, based on our cost constraint here. So that totaled up to 550. Okay, you can see we're sitting at 531 here for our output, 31.33. And we're sitting here with our gradient here at 550. That's why it's a little bigger. But this is where the multiplier comes in, because when it did this partial derivative, it left the lambda here times that 550 amount. The 350 and the 200 where there's unit costs for material and labor here. Put that in, substituted the Lagrangian or in our solution here, and what do we come up with? The gradient here is now take our lambda here. Now that lambda was 0.96, so we take that lambda or our Lagrangian multiplier here, that 0.96608 showing here, times the 550 here, and what does it give us? 531.34. Okay, so that's where the multiplier comes into effect, and you can see that our gradient here for our constraint and the gradient here for our output are equal here, 531.33 here. So you can see that is where the multiplier comes into effect. So that gives us an idea, that tells us the difference between our constraint and our output here, so 531. Now if we further go down over here, remember that Lagrangian multiplier? Just going very briefly here, say I'm not going to go through it all, but if we had an input, we increased our constraint from 40,000 to 40,010, we take it times that Lagrangian multiplier, increased our constraint by 10 units only, times the Lagrangian multiplier. What we're going to get here is that is 9.66, or increase our output. So we're going to increase our output function by the amount by whatever we put into it. If we put 100 in, we'd increase it by 100 or 1,000. We'd get whatever Lagrangian we've calculated at that point here times, and that would give us our increase in our output. Okay, so that's how the mechanics work here, and just looking at it here in the mechanics. So just going back over here, just one last thing here. So again, going back to our production function here, our constraint shown here, and in green that was our level curve here based on our constraint here. So you can see again that f of x here and the g of x here. You can see that that's really the difference. So what we have here, the f and x and the g of x, and we'll go back and maybe look at it the other one. Remember we talked about that the gradients here are perpendicular to they're perpendicular to whatever that tangent line that we shared here between our on the iso curve here and our constraint here. They're perpendicular to it, because that's by definition. They're perpendicular, and they're pointing in the direction here of the maximum output. And then incidentally, this red line here, this red line from top to bottom, that is the gradient path. That's the direction of the maximum output in the case of this function. So maybe let's just go back over here one more time here. Okay, just again, remember we talked about that f of x, and the g of f of x was that we were sitting here at f of x, what was a 531 here? I guess that was 531. Maybe I got these things a bit screwed up here, but the Lagrangian here, I probably should have had the f of x and g of x switched around here. I didn't look at it. But nonetheless, that Lagrangian multiplier here, I had to take that times Lagrangian multiplier times my a gradient here, a g of x, to get up to this terms. I'm sorry, but I think I got the two reversed, but nonetheless, you get the idea here. We come up with that tangent line between our constraint here and our iso curve here, and then we got that maximum point, and nonetheless, you're going to have that Lagrangian multiplier is the difference between whatever output you have in your, in this case, that f of x, and then our constraint g of x. I may have got them reversed here, but nonetheless, that's how it works here. So the Lagrangian multiplier is really used for two things. It's used for adding that artificial variable so we can solve our equations, and then it also gives us the multiplier effect here between our constraint and our output. Just remember here, the gradients here are perpendicular to the level curve, and then the gradients are parallel to each other between our constraint and our level curve. And the Lagrangian, this Lagrangian is really it differs only by the scalar. The difference between our output here and our constraint differ only by a scalar or the Lagrangian multiplier here. Okay, so that's how it works here. So that concludes our discussion.